Shouldn't it be going? Should be streaming. All right. How do I... Me. All right. I'm not sure who's out there because I had a little trouble setting this up, and I don't know if this is the exact same link that I had sent out to the class. So I will wait just about one more minute, probably, and then I'll kind of get started. If nothing else, at least it'll be, I know it'll be captured on video, okay? So at least I'll be able to save it. And I hope the audio is working. I usually have not too much difficulty with this, but today it seems as if I've been having nothing but trouble with this thing. But so be it. Let me just check my other thing that this is working. Oh yeah, okay. So the mic is working. Okay, I can see it. I can see it leveling. Okay. All right. So I was going to talk about the gradient operator. What is going on here? Oh. Now this thing is not... What is going on here? All right. Nothing is working today for me. This is unbelievable. So now it's not updating. Ugh. All right, just bear with me another minute or two. This is not my day. What is going on here? All right, the camera should be going, but yet it's not live. Let me just do this again. Let's see if this goes back on again. Let me try this another way. Ugh. Yeah, okay, now it's back. All right. Ugh, I don't know why I was doing that. This between this and my regular webcam, I've been getting nothing but problems. Let's get it to focus at least. Okay, so there it's focused in. Okay, all right. Well, let's get started then. All right. So again, this is kind of piggyback off of some of the stuff that we talked about in class today, but I'm going to go over a little more the doing stuff, the gradient operator in non-Cartesian coordinates. So I'll do cylindrical and maybe I'll squeeze in spherical depending on how I'm doing. I haven't had too much coffee today. All right. So to do this, let's do a formal definition of gradient operator. So if you think about a scalar field, because this is typically how we kind of approach thinking of the gradient operator. So we'll use the phi, but it's a function of position. So it's a function of the position vector x. All right. And, when you were a sophomore taking whatever, Calc 3, the way you thought of this is you could imagine like isocontour lines in some coordinate system, maybe like our Cartesian 1, 2. And here's a point x in that space. And we want to think of taking the derivative, but in a certain direction. So a directional derivative. Sometimes people call this like a toe derivative. Or actually, it's really a generalization of the Gateau derivative. Derivative. Okay. All right. So if we consider a direction, and we'll define it with a unit vector. So we'll let mu be a unit vector in a certain direction. You can think of the directional derivative, how phi changes in that direction. Consider S to be a metric, like a measure along that direction. And we're going to define that as the limit as delta S goes to 0 of, the regular definition of the derivative, right? Phi at x plus a little bit of something, a delta x, but this has to be a vector delta x, so there you go, minus phi at x over ds. Okay, so ds is the little differential increment along this direction with the unit vector mu, and then obviously we're going to take the limit as that delta x goes to 0. This term here is the value of phi, just a little bit ds down this unit vector direction. This is obviously phi evaluated at the point x over ds, right? So this is just the regular calculus 1 definition of a derivative, but in a particular vector direction, all right? So using this concept, right, we can use the following definition to actually define the gradient operator. So you actually saw this as an undergraduate. But let's consider this vector operator, this grad phi, right, which is the gradient of the scalar phi now. But let's assume for now we don't have this defined, but we're going to use this as the formal definition. So it's the vector operator that when dotted with the unit vector gives you that directional derivative in the direction defined by mu, okay? So this becomes a definition. So if we treat this as sort of an unknown thing, or we want to seek what its form is such that this holds, well, we just think of grad phi as a vector, and so we can think of it as having a component in the I direction times EI, right? And so obviously it's a vector. So that's a general way of writing the vector in index form using our summation notation. All right. So if that's the case, we can revisit this. We can write the unit vector, if you think about it, it has a component in the 1, 2, and 3 direction. And so we're going to write this as follows. All right, so again, we've got a vector here because we've got a sum on the indices, but this is going along the ds direction. So as we change ds, right, if I equals 1, the amount that dx1 changes as we move ds, that's the component of mu in that direction. And like so, likewise, if I is 2, that's going to give us the component of mu in the 2 direction. Right, as we go delta s, dx2 changes this much, so that's its component. Likewise, if we go ds, I should probably call this little ds, right? You know, let's say ds is that amount. Then this component here is going to be how much dx1 changes if we move ds. This component here is how much dx2 coordinate changes with respect to ds. So you see that derivative actually just becomes the components of the unit vector. So I can write this like this with the Cartesian basis EI, right? Now if we do that all together, now I've got d phi ds equals dxi ds in the EI direction. And I'm going to dot that with this definition of phi, but I can't reuse I, so we'll give this a new index. J, right? So there's the J component, EJ. And then obviously if we dot this together, we get a Kronecker delta, a delta IJ here, right? This gives us a delta IJ. The other things are scalars, and so this simply becomes dxi ds, and then the I component of this quantity grad phi, which we haven't defined. All right, so now if you look at this, and you want this to equal this, then clearly, if grad phi I is equal to d phi dxi, I'm sorry, that's supposed to be dxi. Substituting that back into here, you can see the dxi's cancel out, and then we're left with satisfying this equality. So this tells you that the form of grad phi has to be as such, right? So this basically tells you then the I component of grad phi has to equal, being a little careless about my partial and absolute derivatives, but there you go, right? Or in other words, defining the gradient operator of phi, it's going to be partial derivative phi with respect to xi in the EI direction, right? Using the notation again that the comma denotes a partial derivative with respect to xi. Okay? So, you know, we already talked about this class, and you might say, well, what's the point of this? But we're going to use this to define the gradient of phi, and this will allow us to do the gradient operator in different coordinate systems. Excuse me, cylindrical and spherical, okay? All right, so, you know, or I guess I should say, like in class, we defined this nabla gradient operator as being just EI partial derivative with respect to xi, right? By definition. All right. Okay. So, using that, we can do like we did in class, and I won't repeat that, but we could go and, I guess you can't see the bottom of the screen. We can go through and define things like gradient of a scalar field, divergence of a vector field, curl of a vector field, or as we talked about in class today, we can take gradients of vector fields, divergence of second-order tensors, curl of a second-order tensor, right? And we did all that in Cartesian coordinate systems, and that was all well and good. So let's talk a little bit about when we don't have a Cartesian coordinate system, because this does come up quite often in mechanics. All right. So let's do, I guess, the simplest one that's non-Cartesian, and we'll talk about a cylindrical system. And while I see there's a couple people out there, I don't know if you're my students or just random stalkers of mine. Not that I would have those. But I think if you do have a question, you probably can type it in. There's a chat box, and I am looking at that, so if you want to ask a question, but that's fine. So let's talk about a cylindrical coordinate system. Now, again, if you think about being in R3, right? So we're always going to be in R3, right? So that's this space spanned by 3 real lines, R1, 1, 2, and 3. And if we had a position vector, a point in space with a position vector as follows, okay? Now, instead of doing the ij, the E1, E2, and E3 unit vectors, we're going to define a different set of coordinates. And you've seen this, obviously. All right. So we have a metric, well, okay. So if you think about the plane containing the unit vector and the 3-axis, right, we have an angle to that plane. That's theta. The distance projected along the 1, 2 plane is usually given the metric r, right? And then also going up the 3 direction, we have the metric z, right? So you actually define the location of the point by the angle theta, the radial distance out in the 1, 2 plane r, and then the z direction, okay? All right, so if we're thinking about unit vectors, all right, we have a unit vector. I'm going to try to draw this neatly, like at least at this point. Here it is going in the r direction. So that's a unit vector in the r direction. And as theta changes, you see that the position, the orientation of ER will also change as it rotates. Okay. Then we have perpendicular to that, and also perpendicular with the 3 direction, you're going to have a theta component, and it's directed such that as we increase theta, it's going to move in the theta direction, and then finally a unit vector in the z direction. Okay? All right. But the important thing to notice is that their orientations do change as we change position. So as we change theta, notably, the orientations of the, I don't know if I can do it with my hands, the ERs and the E thetas, they all rotate as well. Okay? Which is different than a Cartesian coordinate system, right? So there is a differential. So if you looked at, let's say, let's imagine I've got an initial, I'm going to try to draw this. So this is going to be looking down the z or the 3 direction. And so here is my position vector going to the point x, and then let's say here is the angle theta. All right, so this is the ER direction, and this would be the E theta direction, and then EZ would be coming out of the page, right? So if we were to change theta a little bit by some amount, d theta, these unit vectors would rotate. Obviously, they're still going to stay straight, but they're going to rotate. So this is going to be like ER prime and E theta prime. They perturb a little bit, and this angle change here, we're going to call d theta. Obviously, we're going to take d theta as it goes to 0. All right. So you can see this distance here. Okay, that's a vector distance, and we'll call that d er. That's how much er changes as we perturb it by d theta. If I just change it by d theta, this is the differential vector. So er prime is actually er plus der, right? Okay, so if we do that, we can write that as simply knowing d theta, right? It's d theta, this is the arc length, d theta times the length of the radius. But these are unit vectors, so that's 1. So that's just going to be of length d theta, but it's a vector, so it needs a direction. And as d theta goes to 0, you can see that this has to be perpendicular to ER. So actually that means it's going to be operating in the E theta direction. All right. Likewise, we can look up here, and this is going to be how much, oops, I'm sorry. That is going to be how much E theta changes when we perturb it d theta. And likewise, that is also a unit vector, so it's going to have a length of d theta, but it's moving in the negative ER direction. So there's a minus sign there, ER. All right. So, fine. So we have DER equals d theta in the E theta direction. Or if we divide by d theta, this tells me that DER d theta is actually just the unit vector E theta. And likewise, we can do dE theta. What happens to the unit vector E theta as we perturb it by d theta? And that becomes minus d theta in the ER direction, or dE theta, that's a vector, d theta, equals minus ER. And that kind of makes sense if you think about it pictorially. If we move ER ever so slightly, the amount it's going to move, with respect to the d theta is going to be in the E theta direction. And likewise, if we do the same for E theta, it's going to move in the minus ER direction. So this is the first thing we need to recognize. So as I talked about in class, as we take derivatives of these things, this is actually what the derivatives are. So if you have to take the derivative of ER with respect to theta, it's not 0. It's going to be E theta. Likewise, if you have to take the derivative of E theta with respect to theta, it's not going to be 0. It's going to be minus ER. Okay, so these are kind of important. I hope that you have seen something like that before, but it's always, whatever. It's good to see it again, I guess. Now, the next thing we need to talk about is what is the gradient operator in a cylindrical coordinate system. All right. So if we go back to our original definition that we used on the previous slide for defining the gradient operator, right? It was that d phi ds, right? As we move in a certain direction on the unit vector mu, right? How much phi changes as we move ds in that direction is going to be defined by that unit vector dotted with this quantity grad phi. All right. All right. So just to make it a little simpler, I'm going to actually abandon doing the summation thing so I don't get confused between 1, 2, and 3 and r, theta, and z. So I'll write out the components here. Okay? Maybe this might make it a little easier. So if we think about the unit vector mu, and we're doing it the same way as we defined it previously. So this is going to be how much the measure in the radial direction, xr, in this direction, right, changes with respect to s, and that's going to be in the er direction, plus how much it changes in the theta direction, e theta. Now, this is actually a unit of distance. It's not an angle, right? So that's why I'm putting the little x's here. Here's xr in the r component, x theta, right? Plus how much we move in the z direction, ez. This is the unit vector mu. All right. Now we're going to dot that with phi, and I don't know if I have enough room here, but I'll try to write it small. Maybe I'll wrap it, I guess. I don't know. So, again, assuming that we don't have the form of phi, so there's going to be an r component in the er direction, plus a theta component in the theta direction, and then a z component in the z direction, and that is kind of sloppy. But it's the same as before. It's a little hard to see. That's supposed to be a z. I don't know why I always end up doing this, but again, if we're using this as the definition and we want to find the form of grad phi, this is the radial component, the theta component, and the z component, right? So now when we do the dot product, you can see I got ERs dotted with ERs, ER dotted with E theta is going to give me 0, ER dotted with EZ is going to give me 0. They're mutually perpendicular. So once I do this, and this is my proposed definition of grad phi. So once I do this dot product, now I get the following, right? I'm going to get dxr ds, because this only gives us a non-zero component when I dot with this. So I get grad phi r. And then I get, from dotting this component with this component, dx theta ds in the grad phi theta direction, and then dxz ds, and then the z component of grad phi. So I want to find this quantity, this quantity, and this quantity such that this equals d phi ds. All right? And if you think about this, we want this to cancel out this. We want all these to go to d phi ds. So this should be d phi dxr. This one should be d phi dx theta, and this one should be d phi dxz. All right, so this is where we always pick up the 1 over r. So if you look at this, right, obviously this xr is just going to be my metric r in the radial direction. Xz is going to be the metric in the z direction, or just the z coordinate. But this x theta is not theta, because theta is an angle. It's the measure along that direction. So this, in fact, has to be r d theta. Okay? So if that's the case, then what we have here, I'm running a little bit out of space, is now, maybe I can squeeze it in, dxr, or dxr, which is, we know is z, is r, ds, d phi dr. So you can see that just gives me d phi ds. That's good. Plus d x theta d phi oh, I'm sorry, I'm kind of doing this the wrong way. So let's do it this way, right? So this is going to be upstairs. We need an R d theta ds, right? That's the dx theta ds. And then this is going to be times the d phi theta, right? And then, yeah, let's keep this as one more step like this, just to keep it. Oh, you know what? Let me just write this whole damn thing over. Sorry about that. It's late in the day. All right, let me just rewrite this. All right, so what I'm saying here is this result now just becomes, okay, dr ds times this unknown component d phi r, right? This term here becomes r d theta ds times this component here d phi theta. That's what we want to find out. This term here becomes, well, this is just z, so dz ds times its component d phi z. And we want this all to go to d phi ds, right? All right, so if that's the case, then this term here really should be partial of phi with respect to r. This term here is going to be partial of phi with respect to z, correct? But this term here really needs to be 1 over r partial of phi with respect to theta, all right? Because that will cancel out the d thetas as well as the r that comes up here. And this is, again, the one that gets the units right. So then that means that actually the gradient operator in cylindrical coordinate system should be as follows, okay? Partial derivative of phi with respect to r in the ER direction, and I should always put that out here, right? Plus in the theta direction, 1 over r partial of phi with respect to theta, plus in the z direction, partial of phi with respect to z. So that is my definition of the gradient operator in cylindrical coordinate systems, okay? All right, so fine. So now I know how to take derivatives, and I know the definition of the gradient operator. So now I can use this to find out like divergence and things like this in cylindrical coordinate systems, okay? So let's box this as well, right? So I'm going to use this, and remember the fact that der d theta was e theta, and d theta was minus er, right? So we're going to use these two results. We're going to use those two results to figure out the operators, okay? All right. So let's leave that here. Okay, so let's do an example, right? So let's figure out the divergence of a vector field, but let's just do it in cylindrical coordinate systems, okay? So, right. So this means my operator I'm going to have here, let's see how I can do this. What's the easiest way to kind of write this out? I think if I just do it as a big old bracket, it's probably fine. Yeah, let's do it this way. So, all right, so this is going to be the Nabla operator. This is my gradient operator, right? So I'm going to write it as ER partial derivative with respect to R plus 1 over R E theta partial derivative with respect to theta plus EZ partial derivative with respect to Z. And I'm going to dot that with V, which is just VR in the ER direction, V theta in the E theta direction, VZ in the EZ direction. So you can use the index notation on this as well, but I just do it, I'm writing it out explicitly because, you know, it avoids confusion, okay? So what's going to happen first? Well, we're going to do sort of the chain rule on all this stuff. So first, we're going to have this component basically dotted on this, all right? But remember, first, we have to take the derivatives, okay? So this is actually going to be ER dotted with, let me just, so I don't have to rewrite all this stuff. I'm going to call this like big old star just for now, so I don't have to keep writing it. But this is going to be ER dotted with that star, but I have to take the partial derivative with respect to R of that whole thing. And you can see here, this is where the unit vectors are going to come into play. Plus, then this quantity operating on star 1 over R E theta dotted with star partial derivative with respect to theta. Now this is where it's going to come in because both ER and E theta are going to change with respect to theta. So not only do we take the derivatives of the components, but we'll also take the derivatives of the unit vectors. And then finally, finally this term operating on this, so it'll be EZ dotted with all that star stuff, partial derivative with respect to Z. So it's really, this one is the one that's going to cause us some problems. The other ones are straight up because, you know, ER, E theta, and EZ don't change when we move in the radial direction, nor do they change when we move in the Z direction. They still stay in the same orientation, right? You can see it easy if you go back to this picture, right? If we move in the radial direction, like, you know, swing it out here, obviously ER, E theta, and EZ all point in the same direction. Likewise, if you move that point up in Z, similarly. Only when we change theta do those vectors change. So it's only this term that's going to cause me some problems. But let's just do this, okay? So fine. So when I take this with respect to ER, this term here is just going to give me ER dotted with VR, comma R in the ER direction, plus V theta, comma R in the E theta direction, plus VZ, comma R in the EZ direction, right? Then we're going to get this 1 over R E theta. All right, now I got to do the derivatives with respect to theta. So this is going to be a little bit different. So first I have VR derivative with respect to theta, ER, but we have to use the chain rule here. So this also changes with respect to theta. So this is going to give me plus VR. Now the derivative of ER with respect to theta was just E theta. All right? That's all from this term. Now we operate on this term, so we get V theta, partial derivative with respect to theta in the E theta direction. Now we're going to do the partial derivative of this. I'm sorry, this times the partial derivative of this with respect to theta. The partial derivative of E theta with respect to theta was minus ER. So this is going to give me a minus V theta in the ER direction. Now VZ is just going to be, you know, EZ doesn't change with respect to theta, right? So I get just VZ comma theta in the EZ direction. And then finally we get E from this term here, EZ. And this one again, none of the unit vectors are functions of Z, so this just becomes VR with respect to Z in the ER direction, V theta with respect to Z in the E theta direction, plus VZ with respect to Z in the EZ direction. And now you can see most of these unit vector components I didn't have to write out because we're going to dot with ER. So that means only this one survives. So I get VR comma R. All right. Now when I look at this term though, when I do this term, All right. Actually, you can see there's two theta terms. And one of them, like this one, comes about from the partial derivative, the fact that ER changes as we move with theta. So that was absolutely necessary to get this component. And that's where this component comes from. So now we have here 1 over R. That still exists. E theta dotted with these two components. So I get a VR plus the partial derivative of V theta with respect to theta. So you can see you get this VR component, no derivative, right? That stays there. And then plus, now finally, this one dotted with this term. Again, the only one that survives is the VZ, comma, Z. So this becomes the divergence of the velocity field in cylindrical coordinates, okay? And, it's not that hard, but you can see, the math that pops out the additional terms because some of these unit vectors change when we take the partial derivative, okay? All right, so that's kind of the point I wanted to make. Obviously, we can then do this, and you could figure out, curl of the velocity field, or we could do the divergence of a second-order tensor, and we could do all those in cylindrical coordinate systems. It gets a bit much, but you can do it. But probably better is to maybe use that reference that I handed out today, which had them all worked out for you. But this is where they come from. Now we can also do the spherical coordinate system. So maybe I should do that. I'll do that real quick, but I won't go through all the derivation stuff because, well, actually we're not doing too bad on time. But it feels like it's been a long time. All right, so let's now consider the spherical coordinate system. Okay. So the way this one works, it's a little more complicated, but again, let me draw this really big if I can. So again, we're still in R3. All right. 1, 2, and 3. And now, okay, fine. So I have a position vector to some point X, right? And the way we do this is we have a azimuth angle here, which we call phi. And then also we want to the plane formed by the position vector and the E3 axis, this plane has an angle of theta, just like in the cylindrical coordinate system. But ER, instead of being in this direction, is actually going to be in this direction. So this is the radial direction. Okay? So that is the radial direction. And so the corresponding unit vectors is going to be, that's the ER vector. All right. The E phi vector is going to be pointing in this direction. Basically, I know I always have a hard time kind of drawing this, but imagine as we perturb phi, it's going to be the direction that this point moves, right? So it's going to be in this plane here, but moving down perpendicular to R. And then the E theta one is still basically in the same direction as if you perturbed theta, where that point would go. So they're still perpendicular. They move when we change phi and theta. So we have to consider derivatives of those unit vectors, not only with regard to theta, but also with regard to phi. All right? So to do this, it's actually going to be convenient to also talk about this sort of projected length here, which we know is just going to be r times the sine of phi. So we'll need to kind of know that. And let me also define like a sort of a pseudo polar coordinate system, because that kind of makes things a little bit easier. I'm going to call this ER, but I'm going to put a little hat on it because that would be the ER if we had a cylindrical coordinate system. And then we could also do an E theta hat, which would be the E theta direction in a cylindrical coordinate system. But that actually happens to be identically equal to E theta in the spherical coordinate system. So those happen to be the same. This ER is not the same as this ER, right? Okay. All right. So let's try to figure out some of these things. Like we need to get the partial derivative of ER if we change the angle phi. All right. So again, looking at this, you can probably see this already. If we look right down this plane perpendicular to the one E3 hat plane, I should give this plane a name. I don't know what you would call it. But if we look right at that plane, you can see if we perturb R by this angle phi, right? ER is going to move just like it did in the cylindrical coordinate system in the E phi direction, okay? So this is going to actually be equal to E phi. Maybe I could draw a picture. Maybe it'll help. Like if you looked right down that length, you would have, this would be ER, and this would be E phi. And if we change it by a D phi, this would be ER prime, and this would be E phi prime, where this angle here, which you can't see, is D phi, and this is D phi. So again, by the same logic, ER, its derivative as you move in the E phi direction, turns out to be just E phi. Okay, as we move, perturb E phi by D phi, it's going to move in the minus ER direction. So we get D E phi, D phi. That's going to be minus ER. And last but not least, we have to have E theta if we change phi. But if you think about it, if you look at this picture, E theta is always going to be perpendicular to this plane, right? It's going into the plane. And so if we change phi, actually E theta does not change at all. So that is going to go and be a unit, a zero vector, all right? All right. All right, so that's pretty much the same as it was in cylindrical coordinate system. Now, for doing, we also need to find these with respect to the coordinate theta. So you could do ER as we change E theta. Now here it's a little bit trickier. So what I want to do here is I want to write this. I'm going to substitute in for ER, and you'll see why in a second. I'm going to use this hat system. So this is going to be, again, looking down, straight down. If I look straight down, I'm going to have, this would be ER hat. This would be E theta hat, which also equals E theta. And this is the angle theta. So if we perturb it by D theta, you know, we can see what's going on here, right? But actually, I don't want to do that. Let me get. Actually, what I want to do is I want to get ER in terms of E phi and E theta. So also we can see that too. So if we look this way, like right at the plane again, we'll see the following picture. Here is ER. Here is E phi from the spherical coordinate system, and ER hat is going to go right out this way. All right, that's ER hat, where this angle is phi, and likewise this angle is phi. So that allows me to write ER in terms of, well, let's do its friend going up here, would be EZ hat. So that's going to be, let's draw it up here, E, Z, hat. All right? That sort of false or unused cylindrical coordinate system, okay? So I can write ER in terms of EZ hat and ER hat. So that's going to be cosine phi in the EZ hat direction plus sine of phi in the ER hat direction. The reason why I'm doing this is because I already know these derivatives with respect to theta. All right. And so if I put that into here, this is just going to become partial derivative with respect to theta cosine phi EZ hat plus sine phi ER hat. All right. Now, cosine of phi doesn't depend upon theta, nor does sine phi. So those won't do anything. EZ, if we change theta, EZ still stays in the same direction. So this whole term will go to 0. And the only thing we're going to get here is that ER hat, when we change it by theta, moves in the E theta hat direction, right? Moves into the E theta hat direction. As we move ER hat with respect to theta, it goes into the E theta hat direction, which is actually equal to E theta. So this term will disappear, and all we're going to get here is sine theta in the E theta direction. So, and this is the E theta in the spherical coordinate system. Now, you can do the same thing for E phi, right? And I'm getting a little tired, as I think some of you guys are. So I'm going to just kind of jump to the chase here. You could do the same thing here, where we say that E phi is equal to cosine phi ER hat minus sine of phi EZ hat, and then take the derivative with respect to, I'm sorry, this should be a theta, with respect to theta, and you will find out that this is just going to give you cosine phi in the E theta direction. And then we can also get DE, what am I missing? DE theta as we go in the theta direction. Well, this is exactly the same as sort of the cylindrical, right? So this is E theta is the same as E theta hat. So when we move theta, we know that E theta hat actually goes into the minus ER hat. So this is going to actually become minus ER hat. Okay, now we don't want it in terms of hat, but we know how to express that in terms of ER and E theta. So that's going to be minus ER is going to be cosine phi in the E phi direction plus sine of phi in the ER direction. All right, so that tells us that the partial derivative of E phi with respect to theta is going to be minus cosine phi E phi minus sine phi ER. All right, and so now you got all those metrics lined up. Actually, as you change in R, once again, it doesn't change any of those things. So those all go to 0. So now we know how to get the unit vectors when we change phi, and also when we change theta. Okay? All right. All right, so the last thing we need to do is to get the gradient operator in terms of spherical coordinate systems, and then I am going to call it quits. But from that, you can kind of crank through everything. All right, so let's do that again. So let's find, it's going to be the same approach. Let's do the gradient operator, but in spherical coordinates. Now you can see why I didn't want to do this in class. Anyway, so we're going to go back to our definition. So the unit, now I'm going to use, instead of phi, because we have phi as an angle, I'm going to use the scalar field f. Okay? So before we used phi, but that'll get really annoying because phi is, is also an angle measure, right? From the azimuth direction. So instead of using phi, the scalar field, we'll use f, which I probably should have done for everything anyway, but the book uses phi. All right, and this is going to be df ds. This is our definition of the gradient operator. Okay, so when you do this out, again, this is going to have the form dxr ds in the ER direction plus dx theta ds in the E theta direction plus dx phi in the ds direction. I'm sorry, ds in the E phi direction, right? This term here, again, is what we want to find, but this is just going to be grad f in the r direction plus some theta component, and then also a phi component. All right? So there you go. So when I dot those together, all I'm going to be left with is dxr ds times the rate. So sorry. The radial component of the gradient operator in spherical plus dx theta ds, the theta component of the gradient operator, plus dx phi ds, gradient component in the phi direction, right? And this all is going to go and give me df ds. So we want to find these such that works out. Okay, so like before, when we perturb in the in the radial direction, the measure is just going to become r. All right. Now, when we move, let me go back to this picture. Right. So if we move in the phi direction, if we perturb in phi, the distance it's going to move is r times d phi, right? So that gives me, what am I talking about? This should just be dr, sorry. Dx phi is going to be r d phi, right? So you can see if we move this tip in by changing it in the phi direction, the actual amount it moves is the arc length, so it's going to be the radial distance times d phi. Now, when we do in the theta direction, okay, this one's a little bit different. All right, so when we change in the theta direction, whoops, I need to go back to this picture. So when we move this in the theta direction, it's going to be this distance here, that's the radial direction, times the differential d theta. So it's going to move d theta times r sine of phi, right? Because it's, if we move, perturb in theta, the amount this position vector changes is going to be this length times the angle the change in this angle theta, right? So the measure along that is going to be r sine of phi d theta. Okay? All right. So now if we have that and substituting this into here, this into here, and this definition into here, you'll see that we have dr ds times that radial component plus, now I have r d phi ds, and then r sine of phi d theta ds. What am I doing? This is I'm so sorry. This one should go here, and this one should go there. But you get the idea. This becomes the phi component, and this becomes the theta component. All right? It's been a long day. All right. So here's what we get, right? So again, putting this in for d phi, the dx phi, and this in for dx theta up here, right? Then we arrive at the following. We want that to be the absolute df ds. And if that's the case, we can see that this component here is going to be d phi dr. This component here will become 1 on r d df dr df d phi, this is an f, right? And then this component here will become 1 over r sine of phi df d theta. Okay? So again, I'm sorry, I keep screwing this stuff up, but you can see if I use these as these definitions, it'll cancel everything out here, and you'll be left with the partial derivatives df ds. Okay, so that means that, in fact, the gradient operator in spherical coordinates finally gives us the following. Okay, in the r direction, right? Partial derivative with respect to r. All right, fine. In the phi direction, we get a 1 over r to fix the metric of the theta angle, the phi angle. Partial derivative with respect to phi. That's an e phi in front there. And then finally, for the e theta component, finally there, it's going to be a 1 over r sine of phi. That's where that comes from. Partial derivative with respect to theta. And that becomes that operator. All right? So let me just write that all out in one big summary slide. And I'm not going to go through an example because I'm kind of done with all this, but you can do it as well. You can follow it. It takes just got to be really careful with this. So if you wanted to figure out like the divergence in spherical coordinates, you would use this operator. And when you had to take the derivatives with respect to phi and theta, you have to be careful to use these definitions, okay? So just in summary, for spherical coordinate systems, all right, I'll just redraw the system. So there's the theta direction, the phi direction, and this is the r direction, right? So this is ER, E phi, and then perpendicular to that we get an E theta, all right? So again, summarizing the derivatives, DER with respect to phi equals E phi. D E phi with respect to phi is going to give me minus ER. And the partial derivative of E theta when we change phi gives me a big old nothing. Partial derivative of ER when we change theta gives me cosine phi E theta. Partial derivative of E phi when we change theta gives me wait, what am I doing? Oh, this should be sine. Excuse me. This is cosine phi E theta. They're both in the E theta direction. One gives you a sine, one gives you a cosine component. And then finally, I need a little room for this one, so I'm going to put it down here. But it would go there. Partial of E theta, when we change theta, this is minus cosine phi in the E phi direction minus sine of phi in the ER direction. And then lastly, the gradient operator is going to be what I just derived. In the R direction, it's that. In the phi direction, we get a 1 over R partial derivative with respect to phi. And in the theta direction, we get a 1 over R sine of phi partial derivative with respect to theta. All right, and so using that again, we can figure out, you know, like curl of V in spherical coordinate systems or whatever. All right, or you know, this one becomes a real mess, but you can do the divergence of a second order tensor. You can see it on that form that I handed out. Do I have any of this? Just so you can appreciate it. It does become like a big old mess. Oops, yeah, here's an extra one. So, like, you can see on this back page. Right. So, where's the tensor? Okay, so, like, here's the divergence of a tensor, right? So this is it in Cartesian. That was not bad. Here it is in cylindrical coordinates. And then here it is in spherical coordinates. You just get all those terms with the r sine thetas, and then you get the terms that are 1 over r's because of the derivatives and all that. So it just becomes a big mess. Like I said, you could derive this, but you know, you probably don't want to do that. Okay? All right. So that's it. I hope that was kind of helpful. I mean, it's not like you'll end up doing those derivations all that often, but that is where it comes from. I remember, like, when I first saw that, it always seemed like a little bit of mystery as to where that all happened. So I hope that was of some benefit. All right, thanks. I'm done.